comment, a very quick comment, that is, this uncertainty quantification, in fact, it was used, I mean, in a different context to prove rigorous theorems, because it reminds me of interval arithmetics, where you need to make computations, so long computations on a computer, which introduces errors, and sometimes the approximation of the numbers, the rounding off and propagation of the numbers cannot be controlled by the computer. So you need to replace any real number, not by a Taylor expansion, but rather by an interval, which certainly contains the true result, and then to propagate all the algebra on these intervals. This is called the interval arithmetic. So it's, this is why Epstein was involved, in fact, in the first.
I've got to add this. Most of the people who work on polynomial algebra, in fact, came from the interval arithmetic side. And that's exactly what we did. And everyone who did that and tried to plug the interval arithmetics into complex model had to deal with a so-called dependency problem that you have in interval arithmetics. And this dependency problem has two major issues. One is that your interval, especially if you have a 0 or 1 over there, tend to grow very fast when you plug this into your model. And basically, what you have at the other end is an interval that is so large that you have no information. And the reason why people like Bert try to use polynomial expansion is that, in a way, was not rigorous. You always have a reminder that it's not easy to estimate. But you have a much better estimation of the size of your interval again. Okay? So you drop one thing and you recover the other. So we switch completely topic now. And the other thing that is useful if you design space missions is if you know about optimal control. And I would say that you can find hundreds of papers on optimal control with single objective. And in fact, find probably 4 papers on optimal control with multiple objectives. Which means that is surprisingly not something that people really studied that much. But in fact, I believe is very useful because in a number of cases, especially if you deal with uncertainty, it's very unlikely that you have only one quantity to optimize. And as I will explain in a minute, if you just aggregate objectives by a weighted sum, you might fail to capture the actual minimum or the correct Pareto set for your problem. Okay, so let me start from the definition. And this presentation is going to be much more mathematical than the previous one. So I'll try to do my best to make this digestible. Okay, so first definition is Pareto dominance. And Pareto dominance is a fundamental concept in multi-objective optimization. It was introduced by Vilfredo Pareto at the end of the 19th century. Pareto was an economist, and a problem, of course, for economists is always which choice to prefer. And you can have 2 choices that are not one better than the other. Okay? So Pareto introduced the idea of Pareto dominance to explain that one choice is better than another, even if you have multiple criteria that you can use to evaluate that particular choice. And many years later, Nash introduced the idea of equilibria, starting from the equilibrium of Neumann, and so on and so forth. And even that is a way you can choose basically a particular strategy against the other. So the idea here is that you have multiple criteria, And for each one of them, of course, you want to find the best possible solution to your optimal control problem. This is not an optimal control problem, it's a generic multi-objective problem in which you have also some constraints. So you have a vector of criteria and a vector of constraints. And the idea is that if you have two solutions that are feasible with respect to the constraints, okay, and for one of the two, all the objectives are lower or equal to the value of the objectives of the other solution, and for one particular objective, the two values are different, okay, then one dominates the other. And here I'm interested in minimizing the function. Okay? So that's why I put lower or equal. Now, a point that satisfies basically this definition is a Pareto efficient point, and all the other points that instead have higher value of the objective functions are dominated by that Pareto efficient point. Now, typically, if you take all the points that are Pareto efficient, you don't have one point, but you have a set. Again, we come back to the idea that you don't work with single numbers, but you work with set of numbers. So the Pareto set is the set of all the points in decision space or parameter space, the way you want to call it, that are feasible and that are not dominated. And the image of this in criteria space is called the Pareto front. Okay? Now, three guys, actually one guy, when he was doing his master thesis, accidentally formulated and demonstrated these necessary conditions for optimality in the case of a multi-objective optimization problem. So if you have this number of objective functions and this number of constraints, and the point is Pareto efficient, then it satisfies this set of equations. So it satisfies, of course, the constraints, it satisfies this differential relationship, this first order differential relationship, and I can find Lagrange multipliers that actually allow me to satisfy this equation. But these Lagrange multipliers must be very special because they can be larger or equal to 0 for the constraints, but they cannot be all larger or equal to 0 for the objective functions. Later on, so the first one to write this was Karush in his master thesis, and something like 30 years later at a conference, Kuhn and Tucker presented a paper that contained the same thing. Okay? So that's why they're called Karush-Kuhn-Tucker alternative conditions. Now, if you just take the objective functions, there is another quite interesting observation. So you, of course, don't have the constraints here. You just have the relationship for the objective functions. And that relationship for the objective function is, in fact, a constraint on the possible values of the gradients of the objective function. And this leads to quite an interesting theoretical result that says that the Pareto set, not the Pareto front, okay, so the set of points in your parameter space is a manifold and has dimensionality m minus 1. Okay? So if you have two objectives, so this m is 2, this means that the set of points in the parameter space, doesn't matter how big the parameter space is, you can have a 6-dimensional space like your initial conditions, has still dimension 1, which means is a line in the n-dimensional space. And this has a computational, very important consequence, that you cannot just sample your space and hope to hit the Pareto set. Okay? Because in an n-dimensional space, an n-1 manifold has measure equal to 0. Okay? So you cannot just sample, through samples, randomly and find the solution. Okay, so how do I go from that to an optimal control problem? What I need to do is to introduce a control that is any piecewise function that has an infinite norm, that is defining a space with an infinite norm. I have to introduce a differential equation that is my dynamics. I have to introduce some initial conditions. Okay? So this is now my dynamical system. I want to find the optimal control that minimizes all the objective functions, satisfy the differential constraints, satisfy the boundary conditions. For example, I have a trajectory that wants to go from A to B. I want to go from the Earth to Jupiter. And I want to minimize the propellant and the time at the same time. Okay? That's a typical problem that you can have. So, how do I solve this? Well, option one, what I can do is to say, I have a problem in vector form, and I try to devise a method that deals with vector objective functions. That's not Pontryagin Maximum Principle, because, as you might know, Pontryagin Maximum Principle deals with single objective problems. The second option is to say, I scalarize my vector problem, and I go back to a problem that I can solve with optimal control theory. And the third option, which is the one that I'm going to show you, is a mix of the two. So before we go into the actual solution, allow me to explain what scalarization means. And I will start from my favorite scalarization, which is the Pascoletti-Serafini Scalarisation, that basically said that if you have a multi-objective problem with a vector objective function, you can replace that problem with this problem here, in which you minimize a parameter t. And basically what this problem is doing is to say that you want to find solutions that are in this descent cone. The descent cone is moving along this line that is defined by these coefficients a, and is sliding down as you change t. Okay? So you take this cone and then you try to lower it along that linear line until you hit this point, which is a Pareto efficient point, because your Pareto front here is this curve here, plus probably this small piece here. Okay? So if you identify this direction, the descent direction for your cone, and you find progressively solution that satisfy this constraint, so to be within this cone, and you lower the cone progressively, at some point, all the solutions that you can find that are contained in the cone corresponds to this point here, which is on the Pareto front. Okay? So this is an iterative process, and I formulated the same problem in this easier form to deal numerically. Okay? So you want to minimize S, and you want to satisfy this constraint such that your objective functions are always below this value S if multiplied times a particular weight. And the weight here gives you the slope of the rectilinear line. Okay? So this weight tells you if the line is horizontal, vertical, or at a particular slope, and you move along the line. So, important thing, again, is that if a solution is k-minimal, which means that corresponds to this point here, is also Pareto efficient. Okay? So I have now a scalar problem that is equivalent in terms of solution to the initial vector problem. Now, there is another scalarization, which is quite interesting, that is called Chebyshev scalarization, that instead tries to minimize the maximum over this weighted objective function. Okay? As you can see, this is very similar to the Pascoletti-Serafini scalarization, and in fact is similar also geometrically, because you are now moving within this green area and you're trying to reduce the size of this green area until you hit basically the same point. Okay? Now, there is one theorem that says that basically the two formulations are exactly equivalent. Okay? So Pascoletti-Serafini Scalarisation and Chebyshev scalarization give you the same result, but numerically lead to different algorithms, very different algorithms. Now, why are we using this and not just the weighted sum of the objective functions? The reason is that if you just add up objective function, what you get is a convex representation of your Pareto front. This means that you have to assume that your Pareto front is always a convex curve. So you cannot have something like this. Okay, so you cannot capture maybe this part. Okay? While with the Pascoletti-Serafini or the Chebyshev scalarization, you can reconstruct that. Go on. That. Okay. All right. I wish out. All right. So now let's go back to something maybe more familiar to people who do already optimal control. If you ever try to use optimal control, you can go back to Pontryagin Maximum Principle, and if you haven't seen this, but you can formulate your optimal control problem taking a single objective function, because again, Pontryagin was formulated for single objective problems, in the so-called Myers form, in which your objective function is only a function of your terminal conditions. Okay? Like, for example, the final mass. And then you have the other part that is exactly the same. So you have the differential problem, you have your control, you have algebraic constraints, for example, an upper limit on your thrust level, you have initial conditions, and so on and so forth. And what Pontryagin says is very similar to what the Karush-Kuhn-Tucker conditions say. So if you have a point which is optimal, okay, it has to satisfy this differential constraint now on the Lagrange multipliers, okay? And you have some transversality conditions that contain the gradient of your function. Okay, so now we have that if you are able to find a solution, that solution satisfies this problem. And that is a common mistake in a way, because a lot of people develop algorithms that are instead assuming that if you solve this problem, then you find an optimal solution, which is the sufficient condition. That works in most of the cases, but not in all of the cases. All right. Now, how does that look like if we try to use the Pascoletti-Serafini scalarization? Okay, so the Pascoletti-Serafini scalarization takes the vector problem, okay, which is this one, and reformulate the problem in this shape, which means that if I apply it to an optimal control problem in Myers form, I have to minimize this S that now I assume to be at the final state. I still have my differential equation, so this part is exactly the same, but now my objective functions are scalarized. Okay? So they are translated into constraints instead of being objectives. And if I assume that S is a slack variable with zero dynamics, then all this makes perfect sense in the Myers formulation. Okay? Because I have initial conditions, that can be anything I want, as long as I can minimize the final thing. So I decided to write my own theorem on this because no one has ever done it before. And in this case, again, you need to have that your functions are differentiable at the point in which you want to prove the optimality. These are only necessary conditions, so if you have a solution that satisfies this set of equations, which is exactly the parallel of Pontryagin, but with the Pascoletti-Serafini Scalarisation, which means that the transversality conditions must contain a piece of information on the vector function. And here you are where the vector function comes in. Okay? So this is the equivalent version of Pontryagin Maximum Principle when you scalarize the vector function. And the demonstration is actually 2 lines, because if the scalarized version of the vector problem is giving you the same solution of the vector problem, and you apply straight away Pontryagin to this, then you have that, of course, this satisfies, an optimal solution, of course, satisfies these equations. So let me show you an example in which we have the case of a very simple dynamical system in which you start with a velocity which is different from 0, and then you're braking, okay? And you want to brake, and at the same time you want to go as far as possible and arrive at destination with the lowest velocity possible. Okay? So if you brake a lot, then you reach destination with 0 velocity, but you don't go that far. If you don't brake at all, you go very far, but you don't reach the destination with the velocity you want. So if you apply Pontryagin Maximum Principle after you scalarize, you have a number of equations for the Lagrange multipliers. This is your simple dynamics in which you have the slack variable. You start with these initial conditions. You have a limit on your braking ability, okay? So you cannot reverse, basically. And you want to have that this is always larger than 0. So these are your terminal conditions, and these are the transversality conditions that I derived before. Now, I don't demonstrate this here, but the solution in this case is trivial. So up to a certain point t, when you stop braking, your solution looks like this. So you have an acceleration, so you're braking down. Actually, there is a minus here and a minus here. Okay. And if you look at this solution, the Pareto front, trust me, you can do it tonight instead of going dancing, but this is the analytical expression of the Pareto front. So for this problem, the Pareto front looks like this. So at one extreme, you go as far as possible, but there is a minus here because I want to maximize the distance. Since I always work with the minimization problem, I minimize the negative of the distance. Okay? So if I reach the farthest distance, I have the highest velocity. Okay? And if I brake a lot and I stop, I reach the shortest distance. Okay? So you apply the Pascoletti-Serafini Scalarisation, for example, only to one particular point. You go through the equation, and what you find that if you try to solve this problem, in fact, you end up with a final SF, which is equal to -1 if you want this point that corresponds to T1 equal to 0. Okay? So basically, you don't brake. And at the other end, you end up with an SF that's -1/2, which is the case in which you always brake. So if I apply Pascoletti-Serafini Scalarisation, I actually get the results that I expect. So I get the 2 extreme points, which is a comforting result because it means that at least I did that right. But then I need to check that also the Lagrange multipliers are correct. So I have to write my Hamiltonian as Pontryagin say. I have to calculate basically the solution for the multipliers. And I need to check that they are correct. Now, this equation is telling me if I need to break or not break. Because essentially what Pontryagin is telling me is that the derivative of the Hamiltonian has to be 0. Now these two multipliers must be positive, and they correspond to my constraint on the braking ability. So if one of the two is equal to 1, is telling me that I don't brake, so U is equal to 0. And if the other one is different from 0, it means that U is equal to 1, so I need to brake. Okay? So again, going back to this, if mu1 is different from 0 and mu2 is equal to 0, then I don't brake, and vice versa. If the other one is different from 0, then I brake. So this means that depending on the sign of this lambda, I have either to brake or not to brake. And when lambda changes sign is the point T1 in which I stop braking. So if lambda v is always negative, there's no switching point. Okay? So if there's no switching point, it means that I always brake. And if it's always positive, I never brake. So what happens is that if I look only at one extreme of the Pareto front, which corresponds, for example, to the case in which I never brake, the derivation of the equations as I presented give me that lambda v is always negative. Okay? So it means that I never brake, and I end up in the situation in which I am at this point. Okay, so it works in this case. Right, so I managed to derive a way to deal with my multiple objectives. I think I have till 3:30?
4.
4?
4:30.
4?
Yes.
Which means
4, sorry, 4, yeah.
not Glasgow time, huh?
Yes. Well, okay. I was on the Scottish time.
You have 32 minutes left.
Yeah. Oh, I have to talk about it. Okay. So I managed to derive a theory that is telling me what to do if I have multiple objectives and if I want still to solve an optimal control problem. But what I promised before was that I was sort of offering an option that was combining both the solution of the vector problem and the solution of a scalarized version of the vector problem. So let me see how this can be done numerically. Now, if I scalarize the problem, I end up with a single objective, and probably I can use a standard local optimizer to converge to a solution. But one thing I said was that the Pareto set is a set, and the Pareto front is a set in criteria space. So if I converge to one point, I am not really doing the right thing because I'm missing the rest of the possible solutions. So I want the entire point. So how do I do this numerically? Okay, so what I'm showing now is how to transcribe the optimal control problem from an infinite dimensional problem that you cannot solve analytically in most of the cases. It's not like the nice one-dimensional braking problem I showed before, to a finite dimensional problem. And what I'm using is a technique that I developed when I was doing my PhD that is using finite elements in time developed on spectral basis. And if you ever heard about pseudo-spectral methods for optimal control, this is a very similar approach. So the idea is that if I have either the states or the controls, the first thing I do, I take the time interval on which I want to have my optimal control solution, and I partition it into finite time elements. And on each of the finite time elements, I use a polynomial representation of the states and the controls. And this is one key difference with respect to other approaches, I allow these elements to be discontinuous at the edges. Okay? This basically allows me to rewrite the differential equations into an integral form, in which I have here the dynamics, and this is the integrated part of the left-hand side of my differential equations. And in order to do this, I'm using some test functions, or generally called weight functions, that allow me basically to transfer the derivative onto the test functions. Okay? So now I can have basically a lower level of continuity for my states and the controls. Actually, I don't need to have any continuity for the controls. They don't even have to be differentiable. The states do not need to be differentiable, as long as I find a suitable set of functions for my weights. And the other interesting property of this formulation is, well, there are many properties. One particularly interesting property is that the numerical error in this integral is actually ending up into the discontinuity between the boundary points here. Okay? So numerically, what you see is that if you're not integrating very well your dynamics, you see a gap there, and if you're able to quantify that gap, that is what I did in my PhD thesis, you can actually derive an indicator that tells you if you have to shrink the interval or increase the order of the polynomials. The other interesting property is that, that was not demonstrated by me, is that if you use this as a implicit integrator scheme, then what you get is a family of symplectic integrators that work very well with stiff problems. This just to let you know if you're interested. So, as I said, you partition the time interval in finite elements. On each one of them, you take some polynomial functions, and what I do, and this is the other key idea here, is that when you define these polynomials, you define these polynomials on very specific points that are Gauss points, so are the same points that then you can use for the solution of this integral. Okay? Now, these points are normally called spectral points because they are generated with the zeros of Chebyshev polynomials. And this adds an additional very nice property to your integration scheme, and is that you have a minimum number of points to solve your integral, which means that if you use less points, of course, you get a worse result of your integral. But if you use another scheme might need much more integration points to solve numerically this integral. Okay? So it's a way to give a very fast integration of this equation. All right, the other thing you can do is to normalize your time domain, so you can have time varying, time changing problems. This is just a detail. But what happens in the end is that once you use this transcription, your objective function becomes now a sum of a number of terms. This is essentially your Gauss integration formula. Okay, so with Gauss weights, and you add up your terms and you calculate the integral. If you have the Myers form of the objective function, this term doesn't exist. You have only something that depends on the terminal conditions. And your differential constraints now become algebraic constraints that have this form. So this is an algebraic equation, nonlinear algebraic equation. So this means that my infinite dimensional problem now translates into a nonlinear programming problem that I can then scalarize. Okay? So I have now a nonlinear programming problem written in the scalar form of Pascoletti-Serafini, which, if you recall, is exactly what I wrote at the very beginning, which is this. Okay? Okay. So how do I solve this? Well, one way to solve it is, if you're familiar with MATLAB, you take fmin-con and you pass this to fmin-con, and fmin-con gives you a nice solution. Okay? What is the trick? The trick is that depending on the value of this weight, which is the Pascoletti-Serafini weight, you get a different point along the Pareto front. So you need also a strategy to change these weights and to reconstruct the entire Pareto front. So this is very good if you have a local optimizer with a gradient and you want to converge very fast locally, but it's not good if you have, for example, a problem with multiple Pareto fronts, one nested into the other, and if you want to reconstruct the entire Pareto front. All right. So how do we do that? First, a little bit of theory, just 1 second. So you can write this in the same form of the Karush-Kuhn-Tucker condition. So again, if you satisfy now these conditions, you have an optimal point. Sorry, if you have an optimal point, you can satisfy this condition. So how do we actually solve the problem? Not with fmin-con, or not only with fmin-con. So one way is to combine the idea of a vector problem with the idea of a scalarized problem. So we can try to use a method that deals directly with the vector equation and then refine locally the solution with the gradient approach. So we developed this approach in which you sample basically the space, you throw a population of possible solutions, and then you define some descent directions. For example, these are 3 descent directions, and then you associate to each of them one or multiple members of this population, and then you try to converge along multiple directions at the same time. And since I like evolutionary computation, what you can do after a while that you are converging, you can recombine solutions to try to explore more of the Pareto set or the Pareto front, because otherwise you end up always following the same directions. Now, you can do this through sampling and an evolutionary process, but most of the evolutionary processes cannot really deal very well with constraints. So if you try to work with Pascoletti-Serafini, you have the problem that all the objective functions are now constraints. So what you can do is to try to use a different formulation in which, when you use the evolutionary part of your approach, so you're sampling to generate more solutions, in order to decide whether the new samples are Pareto efficient or not, so you want to retain it and then start a local search from each of them, you use the Chebyshev criterion. That is not a constraint, is formulated as an objective minimization problem. But we demonstrated that this is exactly equivalent to the Pascoletti-Serafini. So this means that basically I can start my evolutionary process, generate samples, select the ones that are Pareto efficient, and then refine each of them, switching formulation and going to the Pascoletti-Serafini. Okay? So I generate this population. I know I have a criterion to decide that these ones, for example, are Pareto efficient. Actually, these ones are Pareto efficient because they're dominating these ones. And I can do it using the Chebyshev criterion. And then I can define some directions and then converge along those directions with a local search. Okay, let me skip this. Let me show you some examples. So one example is what we call the Goddard rocket problem on steroid, because it's a multi-objective version of what you find on classical optimal control textbooks. What you want to do is to leave the surface of a planet with a gravity g, and you want to reach a given altitude with the maximum velocity possible using an engine that is always on with an acceleration a, and you want to optimize the steering load. And what we decided to do was to change this problem and add another objective, which is minimize the mission time. So you want to reach orbit in the minimum time possible and maximize the horizontal velocity when we are at altitude h. So you discretize the problem with finite elements in time. You end up with a nonlinear programming problem. You scalarize that with Pascoletti-Serafini and with Chebyshev, depending on whether you are sampling to generate an initial population or you are converging locally. And then you try to find all the points along the Pareto front. And what we want is to have 10 solutions along the Pareto front, very well distributed, and those 10 solutions must contain also the extrema. Okay? Because the extremal points are very important because they are a single objective optimization problem. So the dynamics is very simple. We have these boundary conditions and these two objectives. So final time and minus the final velocity. So what happens is that you have a good representation of all the Pareto front if you run it multiple times. And we can pick 4 of these solutions and see what they look like. And in order to have a proof that we did something correct, we took the analytical solution that Pontryagin is giving us for some of these points, okay? For a particular combination of time and velocity. So first of all, each of these 4 solutions correspond to this ascent trajectory, and of course this takes a lot of time but gives you the highest velocity. This goes up straight, and of course you have a low velocity when you arrive at destination. But what we were interested in was the control law. This is the control law when you go up straight, and the red curve that you don't really see different from the blue curve is the analytical solution that Pontryagin is giving for the single objective case, and the blue curve is the solution that we calculate using the transcription and the scalarization. And you can do that for different, say, descent directions that correspond to different values of final velocity and final time, and you see how the control law evolves, okay? But it's always matching the optimal solution that Pontryagin is providing. The other thing that we tried to do was to do the reverse problem, much more complicated, and see if the approach was working even if one of the 2 objective functions were not on the terminal constraint, because the theory for the moment is only including objective functions on the final value of the state. But in this case, one of the objective functions is on the maximum heat flux during the re-entry of the shuttle. So we have very simple dynamic equations for the shuttle as a point mass that re-enters in the atmosphere. We don't want to have the temperature too high, otherwise the shuttle burns up. And we want to go as far as possible to maximize the range of our descent. Again, we generate a number of points along the Pareto front. Here we have, again, only 10. And for each one of them, we looked at a solution. So you see there is a maximum lift that we can accept because we have a constraint basically on the angle of attack during re-entry, so we cannot go down like this or like this. So this is the time along re-entry. And what we want to do is to either minimize the peak heat flux, okay, or maximize the downrange, so how far we go with our shuttle. And what happens is interesting is here, because you see here that the objective function works also as a constraint. So this is the limit on the heat flux, and for different descent profiles, we have that the heat flux is limited by the objective function that we impose on Q. Here you see how the angle of attack, which is the limit, and therefore we can all go down with an angle that is too bad. Okay, so to conclude, and I have 10-15 minutes for questions. So what I presented is the multi-objective version of classical optimal control. And what I did was to combine two different ways of solving the problem. One in which you scalarize the equations, and then you use a standard gradient method to converge locally. And the other thing is if you use a population of possible solutions and an evolutionary approach in which you sample and select only the solutions that are Pareto efficient, and then at some point you try to converge locally from each one of the solutions along a particular direction using a Pascoletti-Serafini Scalarisation. I presented you the necessary conditions, so we know that theoretically what we're doing is sound, and we also know that if we combine the two approaches, so both the Pascoletti-Serafini and the evolutionary approach that requires a different scalarization, which is the Chebyshev scalarization, we are not doing something wrong because the two are theoretically equivalent. So in the end, you have this hybrid approach that we of course define mimetic algorithm because in the evolutionary community, when you combine gradient plus a sampling process, you have a mimetic algorithm. It's giving us a Pareto efficient solution that span the entire Pareto set, and we could demonstrate they are matching also the analytical solution. And that's it for me. I have a bunch of references if you want in the presentation. Questions?
You show the model uncertainty part, since we have time.
If you want. It's not that short. I don't think I can do it in 15 minutes. But
I asked him, since he left out the model uncertainty part, because he said it was difficult. I said, since there is time, maybe, but he said it's too long.
We need another hour.
Question concerns this Pascoletti-Serafini model, which, if I understand correctly, is able to deal with the non-convex case. But, of course, you must have an estimate of your concavity, possible concavity region, because you are using a cone. So what about the aperture of the cone?
No, in fact, you don't need it because okay. So the cone is always
right with the
like that. Okay. So the reason why you can deal with concave fronts is that you can define this sliding direction. Okay. And this condition, the stopping condition, is satisfied always when you reach the front.
So you end up in a region where the boundary is locally convex. I mean, that is, you intersect the cone and the set only one point.
Yeah, exactly. The point is that if
so you select the direction.
Yeah, the point is that if you add an intersection with this cone, because everything that is contained in this cone, okay, is dominating everything that is here, okay, and is non-dominating everything that is here and here, okay. So if you had an intersection between this part, say, and the Pareto front, okay, then that would dominate this point here, and this means that you have not satisfied this condition, so you didn't reach the end of this slide along the rectangular line.
After you find the Pareto front, then how can you choose a point in this front? You know, it's not maybe an optimal control question, but in general.
Okay, that's another community called decision-making community. There is not a single way to do it. There are a number of so-called preference approaches that you can use. Some people like to have the knee of the Pareto front when it's convex. The knee. Definitely you want to have the two extrema, okay, because the two extrema give you the range. Then which one along the vessel Pareto front you want to take often is not really, sometimes you don't even want to make the decision, because what you're interested in is actually to see how you change the value of your objective while you move along the front. Okay, so some people remember what I said. I mean, the Pareto front is a manifold. Okay? It's not continuous, but it's locally or piecewise continuous. So one way to deal with this is that you can define a fictitious dynamical system that moves along the front. And a friend of mine, what he did, he developed this system so that you can steer along the front. Okay. So here you see a two-dimensional problem with only two objectives. But this approach works also for many objectives. And in many objectives, you can have 30, 50 dimensions. You cannot even see it. Okay. So some people look at the neighborhood and try to move around just to see the variability more than an actual choice.
Okay, so we'll be back here at 5 o'clock for the shorter